In the last lecture, we had actually completed some portion of it while some was left. One portion was that how could we give the proof of this statement that UA minus UB transpose W is equal to this thing, where we know once it is proven, then II gives us an identity vector, while UA minus UB transport with UA minus UB gives us the magnitude square of UA minus UB. But derivation of this line was actually missing. So that is what I would like to show. Now we have this identity that if you multiply a vector x with another vector ct, and that multiplication, is scalar product, where x is a normal Gaussian random vector having a mean mu, and given as ax, given in terms of a standard random variable as ax. You could see we saw also there in appendix. This thing, where this x is given as aw plus mu, where w is a standard Gaussian random vector, mu is the mean, and a is the covariance of this a vector. So this x vector, so this x vector can be written in terms of the standard with aw plus mu. You can also write the standard vector in terms of this representation, but in that case, w will be equal to iw plus 0. So iw is equal to w. So that is what is written here. Acha. Okay. So this was the identity. All right. That if I have some vector n or some vector x and I multiply it with some other vector c, where I know that this x vector is some transformation of the standard Gaussian random vector, then multiplication of this x by c gives us this thing. Now in our case, if you could see, w was a transformation of the standard. It was being multiplied by this. So now this is the identity. Here I have again reiterated the book point that if mu is 0 and a is equal to I, then x is equal to w. So w is the standard. Now what happens if my w is n naught over 2i? It is 0 mean, but its variance or its covariance matrix is n over 2i. In that case, I would like to write my w also in this standard form, which is as. S is the standard random vector. Instead of w, I have put w here in terms of x, and instead of w, I have put this s standard vector. So this will be some covariance time the s plus mu. because it is also 0 and that was also 0, means this will be 0. I just have to find the value of this A, so that I could write it in terms of standard random variable. And once I write it in terms of standard random variable, I will get my A. Once I get my A, I will just put my A here, and hence I will get the result of my multiplication of the transform Gaussian standard random vector with another vector. So S we all know is 0i. It is a standard. Now W can be written as n0 over 2i, where I'm saying that A will be equal to under root n0 over 2 into I. Because if I do that, then with this representation, I try to find the covariance. So covariance will be this vectors, sorry, the this A vector time its transpose, as we saw here. So the covariance will be A times AT. So I take these values of A, which I have just said here, and I take A and I take its transpose, and you can see that I get my W vector as 0 mean, and covariance comes out to be n0 by 2i. So, so 1 second. So you can see that this transformed vector has a covariance n0 by I, and this was what we wanted. We know that our noise has this covariance matrix, hence this means that its value of A is equal to under root n0 by 2. Now I will just substitute A as under root n0 by 2i. So this will come out to be this thing. IIT is simply I. CTC, you can go back here, is the UA, this is CTC, this is UA minus UB, hence this is proven. Once this is proven, then this proof we have already seen, that you can write all of that the error in detecting UA minus UB, UA or UB vector as Q function of this factor. अब आप सवाल पूछिए. Yes.
सर इसमें हम जो पैरेंथेसिस में 2 आर्गुमेंट्स लिखते हैं, एक मीन होना चाहिए और सेकंड वन वेरिएंस नहीं होना चाहिए, हम उसको कोवेरिएंस क्यों कह रहे हैं?
Actually, covariance is also variance. It is covariance. But there is a very big difference between covariance and variance. And first of all, covariance is found with normally we denote this as covariance of a matrix or a covariance of a vector, and you could see the formula for covariance of a vector was actually a matrix, and it came out to be x minus mu into x minus mu Hermitian, or x minus mu transpose, and then its expectation. So it was giving us a sort of a matrix. That is why it is called a covariance matrix. If you have a vector, then if you want to write in terms of C of n or n, you have to write 0 comma covariance matrix, or you can also say, if you want to represent, you can also represent in terms of variance matrix, but mostly we do with covariance matrix because most of the time mu is not 0. But if mu is 0, then covariance becomes this variance, so they both are same. So this is a form of representation used in the book. You could see here, देखिए ना यहाँ पे, when we come to vectors, so you can see this is the representation of a vector in terms of n, because this was a real random variable. This was the mean, which is a vector, and what is this? This comes out to be its covariance, which we will see ahead. मतलब this is its density function. जी हाँ, क्या कह रहे हैं
सर? मतलब हम अगर वेक्टर्स और मैट्रिक्स से डील कर रहे हैं तो हम कोवेरिएंस में लिखेंगे, यानी मीन और कोवेरिएंस, गॉसियन रैंडम वेरिएबल n। और अगर हम स्केलर्स से डील कर रहे हैं तब हम वेरिएंस शो करेंगे।
यस,
क्योंकि
बट हाँ, क्या कह रहे हैं
सर? मतलब हम प्रीवियसली हम जिस तरह आपने कुछ करवाई थी वेरिएंस विद जीरो मीन एंड यूनिट वेरिएंस, तो हम सेकंड आर्गुमेंट को हम वेरिएंस ले रहे थे, लेकिन अब प्रीवियस लेक्चर से हम कोवेरिएंस लेके चल रहे हैं, मतलब हम आइडेंटिटी मैट्रिक्स।
यानी पहले भी हमने असल में पहले शायद इतने वेक्टर्स आए ना हो, क्योंकि अब वेक्टर्स स्टार्ट हो गए, क्योंकि अब आप डाइवर्सिटी में आ गए ना, डाइवर्सिटी में तो होते ही वेक्टर्स हैं।
ठीक,
तो पर यहाँ पे ये वाली रिप्रेजेंटेशन यूज हो रही, वेक्टर्स की फॉर्म में आपने ये रिप्रेजेंटेशन यूज करनी। हाँ, इफ आपके पास स्केलर है, देन इट विल बी जस्ट ट्रांसलेटेड, म्यू विल बी जस्ट बिकम 0, and actually you are using the same definition for variance, but that is for scalar, and this is covariance matrix for a matrix, for a vectors. It was for a vector, it now becomes a matrix because you will be multiplying n cross 1 with 1 cross n. Okay, so the definition boils down to a scalar case, and that is actually that scalar definition is expanded for a vector case as follows.
जी सर, एक क्वेश्चन है कि जो हम ए और एस यूज़ कर रहे हैं अभी, जो हमने डेरिवेशन की एंड रिजल्ट्स निकाले, सर वो हम किस लिए यूज़ कर रहे हैं? मतलब
अच्छा, wait, have I started recording? Oh, sure.
यस सर,
All right,
ऊपर
all right,
मेंशन हो
thank
रहा
you,
है।
thank you. Yes, ठीक है। अच्छा हाँ, प्लीज आस्क द क्वेश्चन।
जी सर, हम अभी एंड रिजल्ट्स हमने कैलकुलेट कर लिए हैं ए और कैपिटल लेटर ए और एस के, तो वो हम किस लिए यूज़ करें? मतलब उन रिजल्ट्स की बेस पे हमने क्या कंक्लूजन, वो हम क्यों यूज़ कर रहे हैं?
अच्छा,
यानी किन
so
पैरामीटर्स को शो कर रहे हैं?
so we are actually trying to study multiplications of vectors, how the multiplication of vectors changes the overall mean and the overall covariance of that new vector. This is what we are trying to understand. So this is the fundamental. You are multiplying a vector by a vector. Okay, so previously, what was x? X was just mu into AAT, like here, this one. Mu into k, now k is equal to AAT, like this, which is actually x minus mu. If you can see, the same thing is happening in terms of variance, but in variance you don't have a vector, you just have x minus mu whole square, and then it's expectation. But this is a more generalized form. This is for vector. All right, so we just we are just trying to make this point clear. that if you want to do scalar multiplication of a vector with another vector, especially with the first vector is a, standard Gaussian vector or a transformed form of the Gaussian vector, then in that case the multiplication is as follows. So you need to find this A, which is the covariance matrix. Once you know AAT, you can do this multiplication. So in this lecture, what I was trying to show you, that all right, we have this rule, but I need to find A. But how can I find A? I know my vector is as follows, is AS, but I need to find my A. So I said that if your A is this, then the when your W vector will have this zero mean and this covariance matrix, and we know that the covariance matrix of W is equal to n naught by 2i. So previously it was a standard which was n0i. Now it is transformed to a wide Gaussian vector in the real axis. So this is n over 2i. This gives us the proof that your A will be equal to under root n over 2i. So once this is proven, then you can just put the value of A in the equation and you will get the statistics of the product.
सर ये x इज इक्वल टू ए डब्ल्यू प्लस एन, ये कहाँ से रिजल्ट हम यूज कर रहे हैं? जी सर, ये
x is equal to aw plus mu. What I am saying here, that W is a standard Gaussian random vector. Okay, you are transforming it to another vector, you are doing its multiplication and you are adding with a mu. So we have seen that these types of linear translations do not change the the vector still remains a Gaussian vector, but it doesn't remain a standard, because mu is changed from 0 to some other value, and the covariance matrix will change from I to some other value. This is all of this is given actually here. You can this is given here. Gaussian random vectors are defined as linear transformations of a standard Gaussian random vector plus a constant vector. All right.
So
first is standard.
मतलब x is equal to a, इसकी वजह क्या? हम सिंपल हम गॉसियन,
because if you do not know this A, you won't be able to find the other products.
Okay सर, ठीक है, I understand.
अच्छा, now मैं आपको क्या कहने लगा था? So we have done this. So you go to the book first of all, so that you know where we are standing. All right. So we were somewhere here. We had started transmit diversity. We have given its proof. We needed to show that H conjugate H over W is equal to this thing, and we have done this proof in the last lecture. And this I was just started the lecture with this point, and to give this proof that the error was equal to Q into UA minus UB, which I showed you here. We needed this transformation. So after that transformation, you can do all this calculation, and Q comes out to be this factor. So U and UB are vectors. Their mod divided by this will give you the error between two vectors U and UB in the real space. All right, this has been done. All right, so these types of vectors.
सर एक सवाल है.
हाँ जी जी.
सर ये हमने H over H mod क्यों लिखा है सर? Y के साथ.
We have seen this first of all in the scalar detection, that if you want to get your signal, you have to multiply H conjugate over H mod. But there, H was a scalar. Okay. Now what is done? We have transformed our H into H conjugate. So this is called the famous match filter. It is also called maximum ratio combiner or coherent combining, that you are shifting your weights with respect to the channel coefficient that are present in Y. लेकिन ना y के अंदर जो भी h है उसके हिसाब से h लगेगा, तो वो h जो है ना वो h mod बन जाएगा. पहले स्केलर बन रहे थे, अब ये वेक्टर्स के सारे बन जाएंगे. तो ये मैग्नीट्यूड आपका मैक्सिमाइज होगा। जैसे दो वेक्टर्स एग्जैक्टली अलाइन नहीं हो जाते, वैसे एच वेक्टर एच अपने कॉन्जुगेट के साथ जाएगा। क्योंकि इस वाई के अंदर एच घुसा हुआ है, वो एच इस एच कॉन्जुगेट के साथ जाएगा, यू विल गेट एच मॉड स्क्वायर। नाउ दिस इज जस्ट आवर इक्विवेलेंट स्केलर डिटेक्शन, ठीक है। But actually there is also an a full-fledged theory behind why we are doing this, because this maximizes your gain. It's also called coherent combining and all that. We will be also seeing this in a while, if we are able to cover a lot in this lecture also. Okay, if you could see, we have done this, but we did this for coherent detection, and you can see here we did this. Coherent detection, all right. So we said this thing. Yes, so we did the same thing, if you could see, in coherent detection. H over H mod conjugate into Y, because in this case this will become H mod squared, so the magnitude of with X will maximize. Same thing we are doing here for vectors, but greater insight will come when we go through the detection problem in a while. Acha. So now we assume that, all right, my x1, it is BPSK, it could be plus m1 and minus 1. So what will be the probability of error? Now we have seen here in the last lecture that probability of error comes out to be this thing, where now previously it was just UA minus UB mod, because UA UB were just scalars. Now UA and UB, they are vectors. They could be plus and they could be minus A into H vector. So HA, this will minus minus plus HA, this will become 2HA. So 2A, what is this mod? This mod is under root square of first term plus square of second term. जैसे आप लिखते हैं under root x square plus y square plus z square as a magnitude of a vector. Same thing is written here. All right. So this will be h1, h2, h2, h1, 2, h1a whole square plus 2, h2a whole square and all that. So I take just 2a is everywhere. I can take 2a square outside the and radical sign. So it will become 2a, it comes outside. And 2 cancels. I take this under root whole. This becomes a square h mod square 2. All right.
सर h के नीचे डिवाइड नहीं हो जाएगा 2a जब हमने कॉमन लिया?
Common. So what I have done, I have taken this radical sign on both the numerator. It was already in the denominator, so I have taken in the numerator. This will become a square. This will become h mod square. It's simple. इसमें तो कोई मसला नहीं. All right. This under root is both over n naught and 2. This is the same. Now this 2 comes up. We know a square n naught is the SNR of BPSK. So now my probability of error will be given as q into 2 SNR h mod square. All right. So this is, he has again missed the steps. So I have shown you with respect to a vector. Here again you can see that now the error will be definitely smaller, because previously you just had h scalar. Now you have h mod of a vector. Huge difference. There, if once your h was small value, you were in error. But here you have a full-fledged mod value of a vector. All of them, all of these h's have to be very small for this total h mod square to be, small, and hence to be in error. So this is the advantage that has come by using diversity in L branches. Let's try to find the probability of error. What will be the total probability of error given that this is the probability of error for a single value of h? So what is the mean value of the probability? So you know the mean is the same result in of stochastics or of random variables. So you will have this function times the probability distribution of h mod square. Now we know h mod square is just division. Under root square, under root cancel, it is just h1 square by h2 square and all that. So, but you know what is h1 mod square? h1 in turn depends on h1 real and h1 imaginary. So you have actually 2L independent real Gaussian random variables. And h1 mod square is sum of the square of the real and the imaginary parts. So if this is, each of them is a Gaussian random variable, real, imaginary, and then it is in form of a vector. We have done from previous stochastic knowledge and using the Jacobian. We saw if you have a complex Gaussian random vector or a vector, let us say in the x and y axis in orthogonal axis, or in complex domain I and j on I phase and q phase, then its mod square becomes a Rayleigh. Then its mod becomes a Rayleigh. Its mod square becomes a exponential. But here there is another thing. We are saying that we have one mod square, but we have sum of many mod squares. So we are actually summing up, because one mod square is exponential. So what we are doing, we have a new random variable which is summing up those exponentials. So what will be the new random variable? Which is sum of exponentials, and that is called the chi-square distribution. This is another random variable, the third random variable. So you should maintain your progress. We went from a scalar to a Gaussian to a complex Gaussian to a Rayleigh to a exponential, and now we have finally the chi-square distribution. Again, the proof is not given in the book. Okay, so I will first of all go to my notes.
Sir,
Yeah.
2L की समझ नहीं आई किस तरह है. सब्सक्रिप्ट में 1 आ रहा था, लेकिन हमने इसको 2L रियल और कॉम्प्लेक्स की बेस पे.
All right. So you know there were L diversity paths. Is this clear?
जी सर.
Size of H was L cross 1. Is this clear?
Yes sir.
All right. Now what is the value of a single H? Single H is a complex Gaussian random variable, CN01. Is this correct?
Yes sir. Rayleigh कैसे आपने?
Rayleigh था मगर standard था ना 01. All right.
जी जी.
So each C of n consists of real and complex random variables, which are all independent. So total you have LH, but each H has two independents. So total will be L into 2. So total degrees of freedom will be 2L. That is why this is called a chi distribution of 2L. देखें लिखा हुआ है 2L independent real Gaussian random में तो 2L होगा ना. हाँ, if I say how many independent complex Gaussian random variables, you will say L independent complex. ठीक है. But here we are saying how many independent real.
Yes sir, समझ आ गया. जी.
So there are 2L independent real. ठीक है. So when you are studying, from a stochastic point of view, all right, then you can just say, once I have taken, I started with random variables that are orthogonal. So if each of them is independent, I can very well write their joint distribution in terms of a vector as a chi-square distribution. All right. So this is actually written in terms of stochastic course. Right? I think you have studied a chi-square distribution in your
yes sir, इसमें gamma function आता है.
सर हमने इसका ना जस्ट एंड रिजल्ट पढ़े हुए हैं.
जी जी. नहीं, पहला सवाल उनका गैमा, इसमें गैमा नहीं आएगा. गैमा आता है एक जिसमें आता है, उससे थोड़ा आप कंफ्यूज कर गए. चाय स्क्वायर में नहीं है, चाय स्क्वायर की ये डिस्ट्रीब्यूशन. अच्छा, अब आप क्या कह रहे हैं? सेकंड सवाल का.
हाँ जी सर, इसमें ना हमने एंड रिजल्ट्स पढ़ा हुआ है, चाइस की डेंसिटी बस पढ़ी, पीछे बैकएंड पे जो प्रूफ है ना डिटेल वो नहीं पढ़ा होगा।
चलो बस आज वो कर लेना ताकि काम खत्म हो जाए, ठीक है। Now let us see. Now what is this new random variable, which is h mod square? So you know, if you want to be very exact, you have to take a L size random variable, but you know, solving exponential L times, it will become, you know, more mathematically difficult. Then, you know, to find its Jacobian, also very difficult. So I take the short form and I say that my random variable is just the sum of two exponentials. All right. So we know each exponential is a is actually you know, square magnitude of two Gaussian random variables which are orthogonal to one another, or in the, you know, real and complex space. So x1 y1 square, and this becomes, you know, this will become z1 square. This will become exponential because magnitude square is an exponential. This also becomes an exponential, and then summing these two exponentials, which I just say are a and b, I give my I get my chi square distribution. All right. Now let us see how can I get that. So I just assume that my a is an exponential random variable. All right. And you know, exponential random variable is given as 1 over mu e minus mu. Now previously we know our mu was, I think, a square plus n naught. It could be anything. Okay. This book, ठीक है, this यहाँ पे जो book is, what is this book is doing here, he is taking mu to be equal to 1. All right. And I will tell you why he is taking 1, because you know his Cn, when of h, you know, hcn is equal to 0, 1. So the variance actually becomes the mean of the exponential, as you can see in the previous lectures. That is why he has taken 1, 1. But if we want to be exact, if you want to compare this with our previous proofs, there it was a square plus n naught for non-orthogonal modulation. So there we could put for non-coherent modulation or for orthogonal scheme. So this you could put also this to be a square plus n naught if you are building up your child distribution from that perspective. So I take two distributions, okay, all right, and they have the you know, means are the same, mu mu, okay, but their values a and b, they are different. All right. So this is the distribution of f of a, and this is the distribution of f of b. So what I want the distribution of z. Okay. So so what should I do? I apply the same method, the Jacobian method. I form two functions. One function is z is equal to a plus b. This plus this random variable. This is the original random variable, but I form a dummy function, and that is w is equal to a. So I have these two functions. You know, I need two functions, so I have these two functions. All right. Where a is again this random variable having this distribution, b is this random variable having this distribution. All right. So so I need the roots for the Jacobian. So how can I get the roots? So read a is simply equal to w, but b will be equal to z minus a, but a can be substituted in terms of the function z minus w. So both the roots are here and both the functions are here. So I know the Jacobian method, the joint distribution of the, you know, the joint distribution of the given random variables functions divided by Jacobian. Then you will substitute the given functions in terms of their roots, right, which is w and z minus w. So I know that f and fb, they are independent, because you can see they are just exponentials, and you know, exponential functions, they are independent, and they have also many other properties. You might have studied in your previous courses. So they are definitely independent. So I can just write them independently. They are just exponentials independently. They can vary because, you know, product or exponential is just of can be written as product of two exponentials becomes the power addition of their powers in the exponentials exponent. So it can be written as FAW into FB Z minus W, the root FAW F minus W. And what is a Jacobian? So Jacobian, again the same method. So I take Z, differentiate with A, all right, I will get 1. I take Z, differentiate with B, I will get 1. I take W, differentiate with A, I will get 1. W with B will be just 0. And Jacobian comes out to be minus 1. So I substitute minus 1 mod is 1. So I substitute in this equation. So I write FAW and FB Z minus W. Now FAW was just an exponential. Remember the exponential function that we studied previously from the Rayleigh distribution. It was again a unit step function. Starting from 0, it was this shape. So I just write for this shape FA for W. So it will become simple 1 over mu, assuming that mu is the mean, E minus W mu U of W. And then I write FBZ minus W. This will be again 1 over mu U Z minus W. Alright, because Z minus W. And this will become Z minus W over mu. So this is joint distribution. I know if I want to find my single distribution from this joint, I will integrate the random variable with respect to the random variable that I want to delete. So W was just a dummy random variable, so I just integrate by W to get rid of this. So I integrate over W, but the question is, what should be the values of the W? That is important, and here the students will make mistakes. U of W was just a unit step function, so U of minus W is like this, and U of Z minus W will be as U of minus W, which will be actually advanced, because U of minus W है तो उसमें plus करेंगे, it will be delayed, sorry, it will be delayed by Z, it will be somewhere here, and U of W is starting from at 0, so the intersection will be from 0 to Z, from 0 to Z by the amount that you have delayed it. So that is why I will integrate this for the values of W from 0 to Z, because other than these values I can very well see that my product will be actually 0. So the values that will be helpful the values of W that will be helpful will be only going from 0 to Z. So now I do this thing, integration. So this thing is common, not dependent on W. I can take it outside. Inside I have this thing. E of Z minus mu. This is all right. Minus C. अच्छा ये थोड़ा सा इसमें माइनस इसमें कॉमन है, तो ये माइनस में जाएगा तो ये प्लस हो जाएगा, तो ये माइनस W है और ये प्लस W, तो दे विल बोथ कैंसिल, you will just get E of 0, this will be 1. Then 1 of dW will be W, limit 0 to Z will be just Z. So you will finally get 1 over mu square, because there were 2 mu's, into Z into E minus Z over mu. This is what you will get. Alright, where Z is a new random variable and it also comes here, and mu is the mean of your exponential. So next lecture में जाना होगा. Here sir, just for your revision. अच्छा हाँ, कुछ कहना चाह रहे हैं आप?
सर प्रीवियस बस इसमें z का बता दें, हम 0 से इन्फिनिटी नहीं लेंगे जिससे हम प्रीवियसली करते रहे. ये 0 से 2 का ही हम लेते थे इंटरवल, और 0 से इन्फिनिटी.
बिल्कुल, वैसे तो आप 0 से इन्फिनिटी लेना चाहिए ना, कि आपको मार्जिनल डिस्ट्रीब्यूशन कब आएगी, जब जो डमी रैंडम वेरिएबल है उसकी तमाम वैल्यूज पर आप इंटीग्रेट करेंगे, फिर आपके पास मार्जिनल डिस्ट्रीब्यूशन आएगी. यू आर वेरी राइट. ऑलरेडी यू डू 0 to infinity. But if you go above Z, the product will be 0 because the unit steps will not be existing. Their product will not exist beyond Z. So you have to integrate from 0 to Z. All right.
मतलब सर गलत होगा अगर मैं इन्फिनिटी में करूँगा?
अब इन्फिनिटी से
Solution
करेंगे तो
approach
जवाब आपको यस सही नहीं आएगा, जाहिर जवाब सही नहीं आएगा ना आपका, क्योंकि आप इन्फिनिटी तक इंटीग्रेट कर नहीं सकते क्योंकि उसके बाद तो 0 है ना, और आप इन्फिनिटी का फैक्टर जबरदस्ती यहाँ पुट कर रहे हैं, वहां तो प्रोडक्ट एग्जिस्ट ही नहीं करता Z के बाद। जो कॉमन पॉइंट है दोनों यूनिट स्टेप्स का वो 0 से Z तक है, तो यू हैव टू इंटीग्रेट टिल 0 to Z, not with 0 to infinity. Even if you do the integration, then you have to finally come back to 0 to Z because above Z all the values are 0 of the product of two exponentials.
जी सर, और एक और क्वेश्चन था, ये जो लास्ट स्टेप ब्लॉक है ये ज़रा बता दें किस तरह है, जो आखिरी स्टेप फंक्शन है 0 से Z।
जी, तो ये हो जाएगा Z का इंटीग्रल W की लिमिट 0 से जी
सर फिगर में जो राइट साइड पे बिल्कुल ये
अच्छा
वाला
अच्छा,
सर।
ये देखिए ना, ये U ऑफ W है, 0 से स्टार्ट हो रहा है इन्फिनिटी तक जा रहा है।
जी सर।
U ऑफ माइनस W क्या होगा, 0 से जाएगा माइनस इन्फिनिटी तक जाएगा। फिर आपके पास मसला है Z माइनस W है, आपने पहले फ्लिप किया है उसको, ठीक है, और फिर उसके बाद आपने Z से, आपको पता है जब नेगेटिव हो और आप प्लस करें तो वो एडवांस नहीं करता, वो उल्टा काम करता है, वो उसको डिले करता है, तो आप इसको डिले करेंगे बाय Z। अब ये तो आपका U Z माइनस W आ गया, और दूसरा आपका U ऑफ W तो वैसे ही खड़ा हुआ है जो यहाँ पे, अब इसका कॉमन पॉइंट क्या होगा, वो 0 से लेकर Z तक का कॉमन पॉइंट होगा, बाकी वक्त तो दोनों में से कोई एक 0 है और प्रोडक्ट आपका 0 हो जाएगा।
यस सर।
ठीक है, दिस इज द
सर एक सवाल है
जी
सर, ये दो इंडिपेंडेंट वेरिएबल्स हैं ऐड हो रहे हैं, तो सर हमने लास्ट जो हमने कोर्स देखा उसमें देखा था ये एक दूसरे के यानी कि कॉन्वोल्यूट हो जाते हैं जो इनकी आती है, तो हम उस तरीके से भी कर सकते हैं।
आप जिस तरह से मर्जी करना करें, जो भी स्टोकेस्टिक के मेथड्स हैं आप बिल्कुल उनसे कर सकते हैं, हमें जो कोई इतराज़ नहीं, बट मैंने चूंकि हमेशा ये जैकोबियन मेथड ही फॉलो किया, ठीक है, कॉन्वोल्यूशन करना भी आपको पता थोड़ा सा मुश्किल है, या उसको फिर आप फ्रिक्वेंसी डोमेन में ले जाएं, फिर एक और चक्कर होगा। तो
सर ये रिजल्ट जो बन रहा है ना, ये कॉन्वोल्यूट ही बन रहा है। अगर आप थोड़ा सा देखें सर, ये जो रिजल्ट बन रहा है E माइनस म्यू W ओवर N मल्टीप्लाई E माइनस Z माइनस W ओवर N म्यू, सर ये कॉन्वोल्यूशन का ही रिजल्ट बन रहा है।
तो फिर ठीक है, आप कॉन्वोल्यूशन से डायरेक्ट कर लें, मुझे कोई इतराज़ नहीं, आप उस तरह कर लें। मैंने चूंकि हमेशा से एक ही मेथड रखा है यहाँ पे अपने तमाम डेरिवेशंस में, और वो है जैकोबियन मेथड। जो ये ठीक है, यहाँ पे अगर आपका कन्वॉल्व से उतने स्टेप्स में आता है तो बड़ी अच्छी बात है, ठीक है, मगर हर दफ़ा ऐसे नहीं होता, इट इज़ ऑलवेज बेटर टू स्विच टू जैकोबियन। जैकोबियन का फ़ायदा, अगर इंडिपेंडेंस है तो जैकोबियन में फ़ायदा ये होगा कि आपके पास फॉरेन इंडिपेंडेंस से एक जॉइंट डिस्ट्रीब्यूशन टूट जाएगी, और फिर टूटने के बाद आपने खाली इंटीग्रेट करना है दूसरे के साथ, आपके पास मार्जिनल बाहर निकल आएगी। दैट इज़ वाई इन इन ऑल द समराइज बुक्स ऑफ स्टोकेस्टिक for communications we emphasize on the Jacobian method, but if you want to do any other method which is given in reference book, you can do that. Okay, my method is that just to point you the easiest method for all scenarios. Now let us go to build our fundamental concepts. Now we saw previously that if you have this thing, it comes out to be this thing, all right, really, and then it comes out to be this thing, the same a square naught carries and it becomes an exponential, and if now we have seen that if we take the mod square values of the the sum of those exponentials, I will get 1 over mu square z e minus z over mu. So with respect to our PU discussion, I will get factor a square and not a square and not here, but now our mu is not a square plus n naught as an orthogonal. Our is 0 1. So that is why we have taken it to be 1. That is why we will substitute mu in terms of 1. So I will have 1, 1, and this z into e minus z. Book has discussed in terms of x. H mod square is x random variable, so no problem. We will write it as x into e minus x, and hence this will come out to be x into e minus x. Now remember our case L was equal to 2. So 2 minus 1 is 1. That is why our case is x e minus x, and 2 minus 1 is 1, and 1 factorial is also 1. But if you don't have 2, let us say you have 3, 4, 5 degrees of freedom, or degrees of freedom are double, but let us say 5 diversity paths. In that case, this will be 5 minus 1, it will be 4, and this will be 4 factorial. Now we have found the distribution of H mod square. Now again we will do the same step as we did previously, that with this distribution I want to find the mean value of my error probability. So again use the formula from stochastic of finding the mean value of a random variable, which is a function of a random variable. So write the function and write the distribution of that random variable for which there is a function here, and integrate over all values of the random variable. Because it's random variable, the child distribution goes from it is an exponential distribution, it goes from 0 to infinity, so you will integrate from 0 to infinity. Again, this is complex, this is difficult, it will again require integration, double integration to आएगी, q की भी आएगी, and again it will have limits. So again I have taken it out of the course. So once we start doing this at the undergrad level, or then we will be able to advance this further. So we will just take this formula as it is, that the probability of error is given as follows after all of that complex integration. Here, just taking on its face value, mu is given as follows, where SNR is again, a square L naught, the same of the BPSK. This probability is plotted in figure 3.6, and here you can see that as L is increasing, probability of error is actually increasing. Plotted here, as L is increasing, probability of error is decreasing for any value of signal to noise ratio, probability of error is decreasing. Or if you take one value of L, signal to noise ratio increase, we know it will definitely increase, but by having multiple diverse branches or diversity paths, you can see the error probability is actually decreasing. Now there are some approximations to this complex formula, and let us see those. First thing I can say that 1 plus mu over 2 is 1 plus under root. This is a mu value. But what is this value? This value we know can be written as this. I take SNR in the denominator. I can make it half. I apply the Taylor series. This becomes minus half, and higher order powers of SNR. I put this value of under root or this value of mu here. So this will become like this. All right. So 1 plus 1 is 2, 2 over 2 is 1, and this becomes 1 over 4 SNR. And if I say that SNR is tending towards higher values, this will decrease, and hence I can write 1 plus mu over 2 as equal to 1. Similarly, I can write 1 minus mu. So mu was equal to 1 minus half SNR, so this becomes minus 1 half, 1 cancels, becomes 1 over half SNR. So 1 minus mu over 2 comes out to be 1 over 4 SNR. So with these proven approximations, I put these values here. So this becomes 1. So the 1 of L is just 1. This becomes 1 over 4 SNR times L. And this permutation problem and this summation of this permutation combination problem can also be given as follows. Again, we won't go into its proof here. So probability of error will be written as this thing times this thing. So probability of error is governed, for any fixed value of L, this will be, a certain permutation combination. This will have constant value, but this will be changing with respect to power of 1 over L, and hence you can see the probability of error is decreasing as the Lth power of the SNR. Previously we just had 1 over SNR. Now we have 1 over SNR times L. All right, now this is an approximate, but we also try to do an approximation with respect to the knowledge that we have learned from our previous Rayleigh fading channel, when we had only a single channel coefficient, when we had had only a single value of h. Now we have L values of h, and they are making up your h mod square. Now if you compare the q value of this diversity with the q value of the single path, the only thing there it was h mod less than 1 over SNR, and you were in error. Now if you want to be in error, you have to have h mod square must be less than 1 over SNR. All right, सारों को समझ आ रहा है this thing, how I arrive at this thing?
No sir, kindly explain दोबारा कर दो
यार ये आप भूल गए, ये हमने लास्ट टाइम किया था, ठीक है ना? प्रोबेबिलिटी ऑफ एरर ये चीज आई है ना
जी सर, यहाँ तक क्यू फंक्शन।
तो ये कब एरर में होगा? जब ये जो अंदर का फैक्टर है वो मतलब के मतलब 1 से छोटा होगा, जब एच स्क्वायर एस एन आर जो है 1 से छोटा होगा, जैसे हमने पहले किया था। पहले यहाँ पे लिखा था 2h मॉड स्क्वायर एस एन आर था, अब ये वेक्टर का मॉड स्क्वायर हो गया है। तो पहले भी हमने किया था कि जब एच स्क्वायर एस एन आर लेस देन 1 होगा तो आप जाहिर है 1 से छोटे होंगे, तो क्यू फंक्शन है उसमें जो वैल्यूज आएगी 1 से छोटी, तो फिर तो आपका एरर बहुत बढ़ जाएगा, फंक्शन की वैल्यू ज़्यादा आएंगी। तो उधर था एच एस एन आर लेस देन 1, तो एच लेस देन 1 ओवर एस एन आर। यहाँ पे हो गया एच मॉड स्क्वायर एस एन आर लेस देन 1, तो एच मॉड स्क्वायर विल बी लेस देन 1 ओवर एस एन आर, देन यू विल हैव ग्रेटर एरर ऑफ प्रोबेबिलिटी, ग्रेटर प्रोबेबिलिटी ऑफ एरर।
ओके,
ठीक है, सेम थिंग हो रहा है। अच्छा, अब ये है, अब आपने जैसे वहां किया था वैसे हमने यहाँ करना है। ठीक है, वहां हमें जब निकालना था, आई वांट टू फाइंड द प्रोबेबिलिटी, वहां पे था h simple h scalar mod square less than 1 over s. How can I find the probability? You said no problem, you will take the distribution of h mod square, h scalar mod square, and integrate from 0 up till 1 over SNR. That will give you the probability that your random variable is less than 1 over SNR. Here you will say already you will take the distribution of your chi-square distribution and you will calculate the probability that it is less than 1 over SNR. So simple. This was your chi-square distribution. So if your x is small, then this is very small number, e of 0 is approximately 1. You can just approximate it like this. And the probability that this random vector is less than 1 over SNR is from 0 to 1 over SNR times this distribution, this approximated distribution. And you do the integration. And you can then put the limits. For 0 it will be 0, but for 1 over SNR, that will be 1 over SNR to the power L. This will be 1 over SNR L. And L into L minus 1 factorial is L factorial. So we have proven that the probability of error comes out to be 1 over L factorial into 1 over SNR L. Now if you compare this approximation with this, so you can see they are roughly the same, but we know that actually this is very much accurate as compared to this value, because here we have done a lot of approximations to arrive at this result. But still you can see that the commonality is that here this was also 1 over SNR L and this is also 1 over SNR L. So probability of error, if you do very much approximation or you do some exact formula, then you again do approximation, gives us the result that the probability of error decreases by to the L power of 1 over SNR. As compared to simple 1 over SNR, it is decreasing 1 over SNR L. This is your chi-square distribution for different values of L or different values of diverse path. But this 1 over SNR L terms can also be driven from a very important perspective. There's also because when you are in industry, you have to remember these thumb rules. You don't have to do all these complex derivations. So the thumb rule that we have to remember now is that even if you have a diverse path, then remember each of the diverse path, okay, are simple, Cn01. And if I want this total to be less than 1 over SNR, then this means that all of these HL mod square, they have to be less than 1 over SNR. But we have seen that one single HFL mod square less than 1 over SR, the probability of that was 1 over SNR. ये आपको याद है, हमने पहले पढ़ा हुआ है. Probability of this being less than E epsilon is epsilon. So probability of 1 is 1 over SNR, and if all the H of L are independent, the joint distribution will be just 1 over SNR times 1 over SNR L times. That is why it comes out to be 1 over SNR L. So this intuition satisfies this approximation as well as the exact approximation, or as well as the the actual approximated formula or rough approximation is satisfied by our intuition. Hadi, if you have any questions, you can ask. All right. So
सर सिलेबस बता दें.
किसका सिलेबस बता दें
सर? यानी कि मिड्स का.
अभी तो मिड होना नहीं, जब होगा तो दिखाएंगे आपको.
सर हम तैयारी साथ साथ कर रहे हैं.
अच्छा, राइट. सो मैंने ना वैसे तो थोड़ा सा चेंज करता जा रहा हूँ उसको, क्योंकि अब हम ये रमज़ान के हिसाब से सारा चलेगा ना चक्कर. I think you can see the screen. So I will upload this updated course outline. So actually we are in the 8th 17th lecture है ना ये वाला. So we have crossed 8, but because we were slowed down first of all by Ramzan, as well as by the first chapter that we had to study. So the course will be up till this point, repetition coding. This point up till we have studied at this point. This will be the course for the midterm up till this point. All right, so I have also indicated here up till this point. This I will also try to update this. हाँ, इसको उसमें डाल देंगे. हाँ ठीक है, आपको वैसे तो मैंने बता दिया है, तो मसला तो नहीं होगा. आप वैसे इंशाल्लाह आपको शेयर भी कर देंगे. ठीक है. अच्छा, now another thing that was remaining. So I will be ending the lecture as soon as, if you have any questions you can ask, because after that I will not take any more time because I have to go somewhere also. If you have any questions you can very well ask.
सर ऑफिस सर वेडनेसडे को ही आपके आवर्स हैं सर? मतलब कि प्रॉब्लम होती है प्रिपरेशन करते वक्त काफ़ी, तो कुछ ऐसे पॉइंट्स होते हैं जो नहीं रिजॉल्व होते, फिर आगे भी अंडरस्टैंडिंग नहीं डेवलप हो रही थी, मतलब एक बैरियर लग जाता है. तो मैं चाह रहा था सर कि अगर आप आवर्स आपके उतने ही रहें, लेकिन आप डिवाइड कर दें ज़रा वीक में 2 दफ़ा, कि हम एक टाइम पे ही आ जाएं, और गिवन टाइम में अगर कोई प्रॉब्लम हो रिलेटेड तो वो समझ लिया करें.
वो मेरे लिए मुश्किल है करना. मैंने इसीलिए आपको एक ही टाइम दे सकता हूँ, उसमें मैंने आपको फ़ोन नंबर भी दे दिया है. तो अगर आपने, वरना ये कि आप क्लास में पूछ लिया करें. और जैसे आपने पिछला सवाल पूछा था, वो मैंने आपको कहा था क्लास में पूछे, तो आपने खैर
क्लियर हो गया था. जी जी, वो आपने जी
वो मैंने थोड़ा सा हिंट दे दिया था वैसे लेक्चर के दौरान.
हाँ जी सर. जी जी.
चलिए खैर, मैं आज मुझे आज जल्दी है, तो मैं लेक्चर खत्म करता हूँ, पर मैं जो है ना वो जो है कर जितना कर सकता हूँ उतना ही कर रहा हूँ, जो नहीं होता तो पहले ही मैं कहता हूँ कि नहीं हो रहा। ऑलराइट, थैंक यू वेरी मच, आई विल एंड द लेक्चर।
ओके सर।